Imagine waking up to find a 2.5 square mile lake with billions of gallons of water has completely vanished overnight. On November 20th, 1980, this exact scenario unfolded in Louisiana when Lake Peigneur disappeared into a salt mine, swallowing 11 barges and 65 acres of land in a whirlpool so powerful it reversed the flow of a 12-mile-long canal. Have you ever wondered how an entire body of water could simply cease to exist in a matter of hours? In this video, we'll investigate the science behind these bizarre phenomena, examining real cases from around the world where lakes have vanished without warning. You'll discover the geological conditions that create these natural disasters and learn how scientists are working to predict when and where they might strike next. By understanding these events, you'll gain insight into the fragile balance of our planet's ecosystems and the sometimes catastrophic consequences of human interaction with natural systems. Whether you're a science enthusiast, a concerned citizen, or simply curious about the world's mysteries, this investigation into disappearing lakes will forever change how you see the bodies of water in your own community. If you find this geological mystery as fascinating as we do, hit that like button and subscribe to our channel for more incredible stories about the strange phenomena that shape our world. Your support helps us continue uncovering and sharing these extraordinary events with viewers like you. On November 20th, 1980, an event occurred that would forever change our understanding of how quickly nature can transform. Lake Peigneur, a 300-acre freshwater lake in Louisiana with an average depth of 10 feet, became the site of one of the most dramatic geological events in modern American history. The lake, which had been a fixture of the landscape for generations, disappeared almost entirely in a matter of hours. The disaster began when a Texaco oil rig accidentally drilled into the Diamond Crystal Salt Company salt mine beneath the lake. The 14-inch drill bit punctured the roof of the mine, creating a connection between the lake and the 300-foot deep caverns below. What happened next was like something out of a disaster movie. Water began pouring into the mine at an estimated rate of 55,000 cubic feet per second, creating a whirlpool so powerful it sucked in the drilling platform, 11 barges from the canal, a tugboat, and 65 acres of surrounding land. The force of the draining lake was so tremendous that it temporarily reversed the flow of the Del Combre Canal, which normally flows out from the lake into the Gulf of Mexico. For a time, water from the Gulf flowed backward into the now emptying lake basin. The event also created a 150-foot waterfall where there had previously been calm water, the tallest ever recorded in Louisiana at the time. By the time the lake stabilized, it had transformed from a freshwater body to a saltwater lake, its ecosystem completely altered, and its maximum depth increased to 1,300 feet at the site of the mine. Vanishing lakes might seem like supernatural events, but they're actually fascinating geological phenomena with scientific explanations. To understand how an entire lake can disappear, we need to look at three primary mechanisms: sinkhole formation, underground drainage systems, and human-induced incidents. Sinkholes are perhaps the most dramatic cause of lake disappearances. These form when underlying soluble rock, typically limestone, gypsum, or salt beds, is gradually dissolved by groundwater. Over time, this creates underground cavities that can eventually collapse when they can no longer support the weight above. When this happens beneath a lake, the water rushes down into the newly formed opening with incredible force. The process can be gradual or sudden, depending on the size of the cavity and the structural integrity of the overlying rock. In Florida, where the limestone bedrock is particularly susceptible to dissolution, several lakes have vanished this way over the decades. Underground drainage systems present another pathway for disappearing lakes. Some areas, particularly karst landscapes, feature extensive networks of underground caves and channels that can act as natural plumbing systems. When a lake sits atop such a network, any disturbance that connects the lake to these channels can result in rapid drainage. This can happen naturally through erosion or seismic activity, or through human intervention. The Devil's Hole in Nevada is a famous example. It's a deep, water-filled cavern that's part of a vast underground system, and water levels in this system can fluctuate dramatically, affecting connected surface water bodies. Human activities have also been responsible for numerous lake disappearance events. Mining operations, as we saw with Lake Peigneur, can inadvertently connect surface water bodies to underground cavities. Similarly, poor drainage management, excessive groundwater, extraction, or construction activities can alter the delicate balance that maintains lakes. In 2011, Lake Peigneur in Russia vanished after a nearby quarry operation disrupted the underground water table. What's particularly concerning is that as human activities intensify and expand into previously undeveloped areas, the risk of such incidents may increase. Understanding these mechanisms isn't just academic. It has practical implications for predicting and potentially preventing future lake disappearances. Scientists use various tools, including satellite imagery, ground-penetrating radar, and geological surveys to identify areas at risk. By monitoring ground deformation, water chemistry changes, and other indicators, they can sometimes identify warning signs before a catastrophic drainage event occurs. When a lake vanishes, the environmental impact extends far beyond the obvious loss of water. These events trigger ecological chain reactions that can permanently alter local and regional ecosystems. The immediate aftermath of a lake disappearance is characterized by what scientists call ecological shock, a sudden and dramatic change that leaves native species struggling to adapt or perish. The microclimate around a former lake also changes. Lakes moderate temperatures in their immediate vicinity, creating cooler, more humid conditions than surrounding areas. When a lake vanishes, this moderating effect disappears, leading to higher temperature fluctuations and reduced humidity. These changes can make the area less hospitable for species that have adapted to the previous conditions. Perhaps most concerning is the potential for these events to create ecological tipping points. In some cases, the disappearance of a single lake can trigger broader ecosystem changes throughout a watershed. The altered water flow patterns, changes in groundwater levels, and loss of habitat connectivity can cascade through the landscape, creating effects that extend far beyond the immediate vicinity of the vanished lake. Understanding these complex ecological consequences is crucial for developing effective mitigation and restoration strategies in the wake of such events. When a lake vanishes, the human communities that have grown around it face immediate and often devastating consequences. The economic impacts can be staggering, affecting everything from property values to local industries. In many cases, communities that have relied on these lakes for generations find themselves facing an uncertain future almost overnight. Property values in areas surrounding vanished lakes typically plummet. Waterfront properties, once prized for their views and access to recreational activities, can lose a significant portion of their value overnight. After the 1980 Lake Peigneur disaster, property values in the area dropped by an estimated 30–40% in the following years. Homeowners found themselves paying mortgages on properties that had lost their primary appeal, creating financial hardship for many families. In some cases, vanished lakes have been sources of drinking water or irrigation for agriculture. When these water sources disappear, communities must find expensive alternatives, often at significant cost to residents and local governments. After Lake Delhi in Iowa drained in 2010 following a dam failure, the community faced an estimated $12 million price tag to rebuild the dam and restore the lake, not to mention the costs of finding alternative water sources in the interim. The fishing industry is particularly hard hit when lakes vanish. Commercial fishing operations may lose their livelihoods entirely, while recreational fishing guides and related businesses see their income streams dry up. The loss of fish populations can also affect food security in communities that depend on local fish as a protein source. Insurance issues compound the financial challenges. Most standard homeowners and business insurance policies don't cover losses from lake disappearances, which are typically considered earth movements and specifically excluded from coverage. This leaves property and business owners to bear the full financial burden of these events. The long-term economic recovery of communities affected by vanished lakes can take years or even decades. Some communities never fully recover, while others adapt by finding new economic drivers or by undertaking expensive restoration projects. The psychological toll on residents, however, can last much longer, as people struggle with the loss of a landscape feature that was often central to their community's identity and their personal connection to place. Throughout recorded history, lakes have been disappearing around the world, sometimes gradually over centuries, and other times in a matter of hours. These events have captured human imagination and scientific curiosity alike, offering valuable insights into geological processes and our relationship with the natural world. One of the most famous historical examples is the disappearance of the Aral Sea, once the fourth largest lake in the world. Located between Kazakhstan and Uzbekistan, this massive saltwater lake began shrinking in the 1960s when Soviet irrigation projects diverted the rivers that fed it. What was particularly striking about this case was the speed of the transformation. By 2007, the Aral Sea had shrunk to 10% of its original size, splitting into 4 separate lakes. The environmental and human consequences were catastrophic, creating a vast desert dotted with the rusting hulks of fishing boats and causing widespread health problems among local residents due to toxic dust storms. In 2007, Lake Alakol in Kazakhstan vanished almost overnight after a sinkhole opened in its bed. The lake, which covered approximately 20 square kilometers, drained completely in less than 24 hours, leaving behind a muddy basin and stranded fish. Local residents reported hearing a loud whooshing sound as the water disappeared, followed by an eerie silence where there had once been the lapping of waves. Scientists later determined that the lake sat atop extensive underground cave systems that had gradually expanded until they could no longer support the weight of the water above. The Guadalupe River Lake in Texas offers another fascinating case study. In 2008, this 250-acre lake suddenly drained after a sinkhole opened in its bottom. What made this event particularly unusual was that the lake had been artificially created in the 1930s by damming a section of the river. The sinkhole exposed the fact that the lake sat atop a complex network of underground cavities, highlighting the potential risks of creating artificial water bodies without thorough geological surveys. Lake Cache 2 in Chile has become famous for its repeated disappearances. Located in the Aysén region of Patagonia, this glacial lake has drained completely multiple times since 2008, most dramatically in 2016, when 200 million cubic meters of water vanished in just a few hours. The lake sits atop the Colonia Glacier, and scientists believe that climate change is causing the glacier to thin, creating tunnels that allow the lake to drain periodically. Each disappearance sends a massive pulse of water down the Baker River, creating flood risks for downstream communities. Perhaps one of the most mysterious cases is Lake Michigan-Huron, which technically constitutes a single body of water despite being divided by the Straits of Mackinac. In 1998, water levels in this massive lake system dropped dramatically and suddenly by more than a meter in some places. While not a complete disappearance, the event was unusual enough to prompt scientific investigation. Researchers eventually determined that a combination of crustal rebound, the land continuing to rise after being compressed by glaciers during the last ice age, and changes in atmospheric circulation patterns were responsible for the dramatic water level drop. These historical examples demonstrate that lake disappearances are not isolated incidents, but recurring phenomena throughout human history. They also highlight the diverse causes behind these events, from human intervention to natural geological processes and climate change. By studying these cases, scientists can better understand the complex interactions between surface water, groundwater, and geological structures that make such dramatic transformations possible. As our understanding of geological processes has advanced, so too have our methods for detecting and potentially preventing lake disappearances. Today, scientists and engineers employ a sophisticated array of technologies and strategies to monitor at-risk lakes and intervene when possible to prevent catastrophic drainage events. Satellite monitoring has revolutionized our ability to track changes in lake levels and surrounding land surfaces. Modern satellites can detect subtle changes in ground elevation that might indicate the development of underground cavities or subsidence that could precede a lake disappearance. For instance, the European Space Agency's Sentinel-1 satellite uses radar interferometry to measure ground movement with millimeter precision, allowing scientists to identify areas where the ground is gradually sinking. This technology has been particularly useful in monitoring lakes in karst regions, where underground dissolution is common. Ground-penetrating radar (GPR) has become an essential tool for investigating what lies beneath lakes. By sending radar pulses into the ground and analyzing the reflected signals, GPR can create detailed images of underground structures, including cavities, fissures, and layers of different rock types. This technology allows geologists to assess the stability of lake beds and identify potential weaknesses before they become critical. In some cases, GPR surveys have revealed extensive cave systems beneath seemingly stable lakes, prompting further investigation and monitoring. Seismic monitoring networks have also proven valuable in detecting potential lake disappearance events. Microseismic activity, small earthquakes, and tremors that are too faint to be felt by humans can indicate stress changes in underground rock formations. By deploying sensitive seismometers around at-risk lakes, scientists can detect patterns of microseismic activity that might precede a collapse or drainage event. This approach proved successful in predicting a drainage event at Lake Peigneur 2 in Chile in 2014, allowing authorities to warn downstream communities. Prevention strategies vary depending on the specific risks identified for each lake. In cases where underground cavities pose a threat, engineers have developed techniques for grouting, injecting specialized cement mixtures into the ground to fill voids and stabilize the area. This approach has been used successfully in several locations, including beneath critical infrastructure in Florida's karst regions. For lakes at risk of drainage through natural underground channels, engineers sometimes construct containment systems, such as impermeable barriers or reinforced linings. These interventions are complex and expensive, but they can be cost-effective when compared to the potential economic and environmental costs of a lake disappearance. Early warning systems represent another critical component of modern prevention strategies. These systems integrate data from multiple monitoring sources, satellite imagery, ground sensors, weather forecasts, and more to provide real-time assessments of risk. When thresholds are exceeded, alerts are sent to local authorities and communities, allowing for evacuation if necessary. Such systems have been implemented in several high-risk areas, including parts of China's karst region and around glacial lakes in the Himalayas. Community education and engagement are also vital components of prevention efforts. By helping local residents understand the signs of potential lake instability and encouraging them to report unusual observations, authorities can create an additional layer of monitoring. This citizen science approach has proven effective in several locations, with local residents providing early warnings of changes that might otherwise have gone undetected until it was too late. As our planet continues to warm, scientists are increasingly concerned about how climate change might affect the frequency and severity of lake disappearance events. The complex interactions between rising temperatures, changing precipitation patterns, and geological processes create a web of potential risks that could make vanishing lakes more common in the coming decades. One of the most direct climate connections involves permafrost thaw in Arctic and subarctic regions. Many lakes in these areas are held in place by frozen ground that acts as a natural container. As temperatures rise, this permafrost begins to melt, compromising the structural integrity of these natural basins. In some cases, this can lead to sudden drainage events, as the thawed ground can no longer contain the water. Studies in Alaska and Siberia have documented numerous instances of drunken forests areas where trees tilt at odd angles as the ground beneath them subsides following permafrost thaw. These same processes can affect lake beds, potentially leading to catastrophic drainage. Sea level rise also poses risks to coastal lakes around the world. As ocean levels increase, coastal aquifers experience higher pressure, which can affect groundwater flow patterns and potentially compromise the stability of lake beds in coastal areas. In some cases, this can lead to saltwater intrusion into freshwater lakes, fundamentally changing their ecosystems and potentially affecting their structural integrity. The human dimension of climate change compounds these natural risks. As water resources become more strained in many regions, due to changing precipitation patterns and increased demand, there's greater pressure to extract groundwater from beneath lakes. This can reduce the natural pressure that helps maintain the integrity of lake beds, potentially increasing the risk of sudden drainage events. Scientists are working to improve models that predict how these various climate-related factors might interact to affect lake stability in different regions. These models incorporate data on geology, hydrology, climate, projections, and human activities to assess future risks. While there's still considerable uncertainty in these projections, particularly at local scales, the general consensus is that climate change is likely to increase the risk of lake disappearance events in many vulnerable regions around the world. When a lake vanishes, the story doesn't necessarily end with the disappearance. In many cases, communities, scientists, and government agencies undertake ambitious efforts to restore these water bodies or adapt to their new reality. These recovery efforts represent fascinating intersections of ecology, engineering, and community resilience, offering valuable lessons about our relationship with natural systems. The Lake Peigneur disaster in Louisiana provides a remarkable example of ecological adaptation following a lake disappearance. After the 1980 event that transformed the lake from freshwater to saltwater, scientists expected the ecosystem to be devastated long-term. However, nature surprised everyone with its resilience. Within a few years, saltwater species had colonized the lake, creating a new and thriving ecosystem. Today, Lake Peigneur supports a robust population of saltwater fish and has even become a popular spot for saltwater fishing, demonstrating how dramatically altered ecosystems can sometimes find new equilibrium. Active restoration efforts represent another approach to dealing with vanished lakes. These initiatives typically involve addressing the cause of the disappearance and then working to restore the water body. The Lake Delhi case in Iowa illustrates this approach. After the lake drained in 2010 due to dam failure, the community raised approximately $12 million to rebuild the dam and restore the lake. The project took several years to complete, but ultimately succeeded in refilling the lake and restoring the recreational and economic benefits it provided to the community. In some cases, restoration efforts focus on creating entirely new water bodies to replace vanished lakes. This approach was taken in Russia after Lake Beloy disappeared in 2011 due to disruptions from a nearby quarry operation. Rather than attempting to restore the original lake, which would have been technically challenging and extremely expensive, authorities created a new artificial lake nearby designed to serve similar ecological and recreational functions. While not a perfect replacement, this approach provided some measure of compensation for the lost lake. Ecological restoration of the areas surrounding vanished lakes represents another important aspect of recovery efforts. When lakes disappear, they leave behind newly exposed land that often requires restoration to prevent erosion, control invasive species, and create new habitat. In Florida, where several small lakes have disappeared due to sinkhole activity, restoration efforts have focused on creating wetland ecosystems in the former lake beds. These wetlands provide valuable habitat for wildlife, help filter water, and offer some recreational and educational opportunities for local communities. Community adaptation is perhaps the most challenging but essential aspect of recovery following a lake disappearance. In some cases, such as with the Aral Sea in Central Asia, complete restoration of the original lake is impossible due to the scale of the changes and ongoing water management challenges. In these situations, communities must adapt to a new reality without the lake. This adaptation process often involves economic diversification, development of new water sources, and psychological adjustment to a changed landscape. The psychological and cultural aspects of recovery are often overlooked but critically important. Many communities develop strong connections to lakes that are central to their identity and sense of place. When these lakes disappear, it's not just an environmental or economic loss, but a cultural one as well. Successful recovery efforts often include elements that acknowledge and address this cultural loss, whether through memorials, educational programs, or the creation of new community spaces that help maintain social connections previously centered around the lake. Looking to the future, scientists and restoration experts are developing more sophisticated approaches to lake restoration that take into account climate change projections and other emerging challenges. These approaches emphasize resilience and adaptability, recognizing that the conditions that led to a lake's disappearance may represent a new normal rather than a one-time event. By building resilience into restoration efforts, communities can create water bodies that are better able to withstand future shocks and continue providing ecological, economic, and cultural benefits for generations to come. As we look toward the future, the stability of our world's lakes emerges as a critical concern that intersects with some of the most pressing challenges of our time. The phenomenon of vanishing lakes serves as a powerful reminder of the dynamic and sometimes unpredictable nature of our planet's systems, challenging us to think differently about how we manage and protect these vital resources. The scientific community is increasingly focused on developing more sophisticated monitoring and prediction systems that can identify at-risk lakes before they disappear. Advances in satellite technology, artificial intelligence, and sensor networks are creating new possibilities for early warning systems that could potentially prevent catastrophic drainage events or at least allow communities to prepare. Some researchers are even exploring the possibility of smart lakes water bodies equipped with extensive sensor networks that continuously monitor conditions and provide real-time data on potential risks. Climate change adaptation will be crucial for protecting lakes in the coming decades. This may involve hardening infrastructure around vulnerable lakes, creating buffer zones that can accommodate fluctuating water levels, and developing contingency plans for rapid response to drainage events. In some cases, it may even mean making difficult decisions about which lakes are worth trying to save and which should be allowed to disappear with minimal intervention. International cooperation is emerging as an essential component of lake protection efforts. Many of the world's most significant lakes cross political boundaries, requiring coordinated management approaches that transcend national interests. Organizations like the International Lake Environment Committee are working to facilitate knowledge sharing and collaborative management strategies that can help protect these shared resources. Public awareness and engagement will also play a critical role in the future of our lakes. As more people understand the value of these ecosystems and the threats they face, there's greater potential for community-led conservation efforts and political will for protective policies. Educational programs that highlight the importance of lakes and the risks they face can help build a broader constituency for lake protection. Perhaps most importantly, the phenomenon of vanishing lakes challenges us to reconsider our relationship with natural systems. These dramatic events remind us that nature operates on its own timeline and according to its own rules, regardless of human plans or expectations. They underscore the importance of humility in our approach to managing natural resources and the need for greater respect for the complex, interconnected systems that sustain life on our planet. As we move forward, the lessons learned from vanished lakes can inform more thoughtful, sustainable approaches to water resource management. By understanding the delicate balance that maintains these ecosystems and the factors that can disrupt them, we can work toward a future where lakes continue to provide their essential ecological, economic, and cultural benefits for generations to come. As we've seen, the mysterious vanishing of lakes is a powerful reminder of nature's unpredictability and the delicate balance that maintains our world's water bodies. From the dramatic collapse of Lake Peigneur to the gradual disappearance of the Aral Sea, these events teach us valuable lessons about geological processes, human impacts, and the resilience of ecosystems. Join us next time as we dive into another geological mystery that will forever change how you see the world around you. Thank you for watching, and remember, the next time you visit a lake, take a moment to appreciate its presence, because you never know when it might simply vanish into the earth.